Yes, right. So the crosstalk is an interference from the nearby Y. Where? Oh, sorry. Okay. So the crosstalk, you have the crosstalk here. Crosstalk. It is interference from the adjacent, Y, right? So you see when you put the Y next together here, you see you have the high possibility that the signal here is leaking out from the one Y and go to the another Y here. That's the crosstalk when you put them next together. You see, put them next together here. So in order to eliminate the crosstalk, what technique you have to do? What do you think? In order twist, twist them together, right?
Twisting the wires, right?
Yeah, you have to treat them together here. You have to treat them together. And one Y have the positive and one Y have negative. And remember here for the UTP cable, you have a 4 pair. You have the 4 pair of the treat here, right? But the thing is that the rate of the treat is not always the same. You see, some of the Y here, the rate is very, very dense here. But some you have the longer rate treat here, not always the same. You can see it from here, right? So with the crosstalk, you have to remember that you have to with the treat cable here, right? Now you have the definition of attenuation. What is it? What is the attenuation here? What is the attenuation? Any idea? Now think about that. At the beginning, you are very strong, right? And if you run a long way here, you exhausted, right? And think about this one. The attenuation here is that it's at the beginning you have very perfect square signal here, right? But if you transmit along the way, it's very long here, right? So the signal here can be degraded or distorted here. Not it's degraded, not distorted. Degrade here. Right? So see, for the specific cable here, you only have the specific length. You cannot transmit more than that. Otherwise, you have no way to detect which one is the bit number 1 and which one is the bit number 0 here. Right? So the attenuation it is a signal degradation when you transmit the signal along the way. The longer cable it is, the more degradation you have. Right? So for the normally for the copper cable, for UTP cable here, or you cannot transmit greater than 100 meter here. That's the thing. What's the latency? What do you think? What's the latency here?
It's the amount of delay, right? In a message.
Yeah. How long do you deliver from the source to destination? You see, in order to deliver from the source to destination here, you take the time. You have to take time here, right? So the latency here is measured normally in the millisecond here. And the round trip time, that means how long do you deliver to the destination and destination accuracy here. Right? That's the round trip time. Now we have the definition for the full duplex, half duplex, and simplex and so. What is a full duplex? What is a full duplex?
Two-way.
Yeah, two-way, right? You can transmit and receiving at the same time. Right? Here, transmit and receiving here. This is and this is and at the same time. Now, what is a half duplex? Oh, right?
Yes. I believe that means it can go both ways, but only one way at a time.
Yeah, right. So you can go both ways, but you have all here, right? You can transmit or receiving. You cannot do it at the same time. And simplex, that means you only transmit it here. Right? This one, or you have this one here, receiving here. So normally this one work with optical here. You have a single cable for the transmitting, and you have a single cable for receiving. Okay. And you can see that I have the simulation here, so you can tell what is a half duplex and what is a full duplex here. So remember that nowadays, one thing here, nowadays, almost nowadays every device they work with a full duplex here. So you don't have to worry about the half duplex. But the thing is that in the legacy, when you connect from the street to the hub here, hub is a half duplex, right? And the street here is you have full duplex. And see, when you connect them together, if you don't change the switch here to the half duplex, you have collision here. Because this guy here transmit and receive at the same time, but this guy only transmit or receiving here. That's why you have collision. And Normally the hub duplex here, it belongs to the legacy. In the part, it works with the hub. The hub is a layer 1 device here. The layer 1 device. It looks like the switch. It looks like the switch, but it works in the layer 1, so it have no idea what is the MAC address. What is the MAC address? So that's why when we send it to the hub send it out to everyone. Send it out to everyone. Yeah, flood it out to everyone here, right? So see, when this guy transmit here, every other one have to receive it. You have no way to transmit it, otherwise you have collision. But for the switch, it's a full duplex. The switch, it know that the switch you have the layer 2 address, right? So it maintains the MAC address table. You did it in the assignment already. You did it in the assignment. So in the switch, switch maintains the MAC address table here. What do you think? What do we have in the MAC address table? You did it one in the assignment already. You look with the packet tracer and you work with the MAC address table here. What do you think? What you have in MAC address table? What do you have in MAC address table? Any idea?
The stored information from all the addresses that you can contacted with, right?
Yeah, it stores the MAC address, right? It stores the MAC address of every computer connected to it, right? That's what I mean. Anything else? Yeah, that is the thing. The MAC address here is always mapping between the MAC address and the port number. It always matching between the MAC address and the port number here. Let me show you the how it works with the switch here. So now you can think that for this one I have the switch here, right? On the left I have the switch here. Alright, so see now see what happened here. Let me bring it here. Okay, so now I want to bring from this one, .10 here, .20, right? So now we see the question here, if you look on the switch, the question here is so if I want to send the packet from this .10 here to the 20 here, the question here, how can switch know? It has to forward it to the port F0/2 here instead of the F0/4 or F0/3 or F0/5. How can switch know? So no, it know because it maintains the MAC address table. And in the MAC address table, matching between the MAC address and the port number here. So we can look here. If you look on the MAC address table of the switch, they have maintained the MAC address table. And to make it short, I just take the number here. Right? So it's matching here 7372 matching with the port number 1. Right? And you have this one here 1D07 matching with the port number 2 here. So see, when you send the packet from the .10, you go to the switch. Switch look it up and he knows that this guy here want to send it to the 1D07 here. And now I just forward it to the port number 2. That the switch work in the layer 2 and it maintains the MAC address table here. Okay, so we can see it here. You can see it in the packet tracer here. So now if you want to look it up in the MAC address table, you have the command here. You have show MAC address table. So see, if you look at this one, see it matching between the MAC address. On the left here, you have the MAC address. You see, on the left you have the MAC address here. You have this one connected to the port F0/1. And this one here connected to the F0/2. So the next time you see, if you want to send from this one to this one, right, you have to do encapsulation. And you have to put what's the definition? You have to put here 1D07 and the source here 7372. So when we send it to switch look it up in the definition here, and he look it up in the MAC address table, and he knows that this one connect to the F0/2, and he just forward it directly to the F0/2. It makes sense? Okay.
This port number is not that port number.
Sorry, say again.
Port number is not that port number indicates application. So this is
No. The port here is a physical port. Yeah, the port here is a physical port. That's a layer 2. And the port we talk about application is a layer 4. The port in application is like about logical port, not physical. Here is a physical port. Port in the application is the logical port. So it can be the 25 for the email or 80 for the one-way web service here. All right, okay, good. It's good to ask here. Anything not clear, you have to raise the question. That's all. So now we come back to the definition, come back to the simulation of the hub loop like here. Now see, on the left here, I have the hub. The hub is the layer 1. You have no idea what is the MAC address here. All right. So in the hub, it works with the hub loop like here. In the hub here, it works with the hub loop like that. Means when you send to hub send it to everyone, and you have no way to transmit both of the computer transmit at the same time. If one computer transmit, every other one have to listen. You have no way to transmit at the same time, otherwise you have collision. Okay. So now let me do the simulation here so we can see how it works with this one. This one, I want to bring from this one to this one. And I want to bring from this one to this one. So now I go to the simulation here. Now we see what happened here. You have collision here. You see, you have the collision. You see, you can come back here. You have a collision for this one here. And let me delete it first. Fire. Yeah, the fire, that means collision. So now let it do again. I have bring this one. I have bring this other one here. Now simulation. See, send. Send here. You have the fire. You have collision. That's why you are not able to transmit it at the same time. You see, you cannot transmit from this one to this one and this one to this one at the same time. You cannot do it in the hub here because hub is a hub loop like. Now what happened here? Let me do it again for the simulation here. So what happened here? See, when you send to the hub, what happened? You can look in the frame of the hub. You see, in the hub, you have no idea what is the MAC address here. Right? You have no information about MAC address. It's totally is a layer 1. It only is everything about cable here. You have no idea what is the MAC address. So that's why you see. That's why when you send it to the hub send it to everyone. Whenever you send it to the hub send it to everyone here. You can see it here. Right? Send to everyone. Send it to everyone here. Right? That's why. And this one is not correct. This one not correct. That's why this one receive it here. That's why the hub here it work with the hub loop like here. Hub loop like. When you send, everyone have to listen. You have no way to send from here and send from here at the same time. Okay. Now, if you come back to the switch it is layer 2. It understands about the MAC address. That's why it works with the full group like here. Now see, if you come to the left here, I come to the full group like here. Now think about this one. I make it smaller so we can see it. That is a MAC address. So now, in the switch here, right? If I want to send from this PC to this PC, and I want to send from this PC to this PC here, I am able to do it at the same time. I am able to do it at the same time because the switch is layer 2 here. So you can see, send it to the switch. So we look on this one here. If you look on the frame of the switch, it is the layer 2, right? You see, you have both of the layer 1 and layer 2. And you see, in the layer 2 here, he want to send to the 1D07, it's matching with the port F02 here. Right? So it's very straightforward here. And how about this one also? If you want to send to the DC1C here, you send it to 03 here, right? 03 here. So that's why the suite is a layer 2 and it works with the MAC address table. That's why it works with the full loop like here. You're able to send and transmit at the same time. It doesn't matter. It doesn't matter here. Okay. Now, we have definition of multiplexing also. What is the multiplexing and what is the benefit of multiplexing? What is it? Multiplexing here. Why do we need to use the multiplexing? And what's the benefit? Any idea?
Isn't multiplexing so you can like communicate multiple signals at the same time?
Yeah, right. See, you think about this one, you have the one computer here, right? You have only physical cable, one cable here. But at the same time here, you can use for the World Wide Web or the email here, right? The email here. So in that case, you have to work with interleaving them together. You have interleaving signal together, right? Okay, so we can think about this one. You break it down the World Wide Web here into the 1, 2, and 3 here. 1, 2, and 3, right? And for the email here, you can break it down into the 1, and 2, and 3. Right? Now use the multiplexing them together, interleaving them together, right? So the first one here, for the first one, you have number 1 from the World Wide Web, right? Now the second one, you take it from the email and so on. Right? So interleaving them together. So you see, by using the multiplexing here, you at the same time you can handle all multiple traffic at the same time, right? Now we move to the couple cable. Couple cable, you have the how many type of couple cable here? What do you think? How many type of couple cable you learn? What are they? What are they? What are they?
I mean, copper cables are just the ones that the type of cables that we use to send those electrical signals between, right? Or are you looking for more?
Hello? No.
You send the signals between copper cables, right? Or are you looking for something more?
No, I'm working specifically for the couple cable here. So for the couple cable, you have the 3 types of couple cable. Right? What are they?
Coax.
Yeah, right. The first one is coaxial here. Coaxial. Coaxial, think about it, you work with a television cable, and nowadays use the television cable work as a internet cable here. The second one you have UTP, right? And the third one you have the FTP here. Right? So normally for the home internet, the most common here is a coaxial cable. It works from the television cable, right? And you have the UTP and FTP here. So now, when you come to the UTP and FTP, the UTP is the most common cable you use in the local area network. You can see here, it's this class here. The most common here you use in the local area network. So what is the difference between the FTP and UTP? What do you say?
It's shielded and unshielded, right?
The U here is unshielded, and F here is the shield, right? So that is the most common. You have the UTP, and you have this FTP here. This one is shield, and this one unshielded here. And this one is the most common one, right? The reason is the most common one is very cheap and easy to install here, right? But the thing here, why do you need to use the shield? Why do you need to
protect the data? But
it protects from the external interference, right? So you think about in the case that you work in the manufacturer, you have a lot of machine going on here. You have a lot of electromagnetic noise or radio frequency noise here. You have to protect it, right? So that's why instead of the cable here, you have the outer foil to protect it, and for each of the pair also you have the foil to protect it here, right? And from the performance point of view, from the electromagnetic point of view, FTP and UTP work the same. work the same. How they terminate it, how is the pin location, totally the same. The only thing is that this one is show it from the external interface here, and of course this one is more expensive and harder for you to implement here. Okay. Okay, so now you also learn something about the terminator and cable pin out here. For the FTP and UTP, for FTP and the UTP, what type terminator you use? What type of terminator you use? What do you think?
Terminators indicate, wait 1 second.
So you have a cable, right? You have a cable and you have to terminate it. So what is the name of the terminator here? RJ45. RJ45, right? They call it a terminator. Here it's RJ45 here. 45. RJ45. And in order to terminate it, you have two standards. You have two standard here. The first one is a 568A, and the second one you have a 568B. And the difference is only about the cable pinout location, how you terminate it, you terminate it here. So I think I can show you in the slide here. Yeah. That is going to, sorry, that is the still here. You have the point here. Yeah, you have two standards here. You have two standards, 568A or 568B. And you terminate into RJ45. Terminator here. And you see, the difference between the A and B is only about the location when you terminate of the pin here. Right? That is everything you work with the A, so we have white, green, or green, and so on. And this is a B here. You have the white, orange, and orange. But remember here, when you work with your network, if you work with A, every computer have to stick to A. You have to consistent here. Right? Or if you work with a B, every computer you have to terminate with a B here. Sorry, every cable you have to terminate with B. You have to consistent with this one. And from the performance point of view, have no difference. Yeah. Okay, so we also have a PoE also. What is it? Power over Ethernet. Power over Ethernet, that means, you see, normally you have the switch here, right? So if you think about, you have the CCTV camera here. Right? So basically, when you have the camera, I'm not really good at the drawing. So when you have the camera, normally you have the dedicated power line to connect it to the power cable to the one socket here. But if you work with the power over Ethernet now, each interface of the switch here, some interface, when you connect the cable, at the same time you can deliver both of the data and the power here. Yeah, and the power here. They call it power over Ethernet here. Now, talk about the copper cable, and the other one is the fiber optic. It's everything about transmitter line here, right? And you have the two category of the fiber optic. You have the single mode and the multi-mode here. What is the difference between the single mode and multi-mode here? What do you think?
It means one like source goes through, and the multi means both power and internet can go through at the same time.
Mm-hmm. Right. So single mode, when you work in single mode here, the core is very small. It only from the 8 to 10 micro meter here, right? Micrometer. It's very small. That's why you only have one ray of light. You only have one ray of light for this one here. So when you have one ray of light, you don't have everything with the reflection much here, right? So in the case of in the case of multimode, this one is very bigger when you compare this one here. And that's why for the multimode here, you have many ray of light when you travel along the way here. You see, when you go with this single mode here, that's the first thing here. The single mode you have one ray of light, and for multimode you have more ray of light here, and they come in the different angle here, right? Not only the same angle here. So that's why for this one here, the single mode here, you can transmit along the way. For this one, it can support to the 100 kilometer here. Is a long way here. This one is not more than 2 kilometers here. That's the difference here, right? And this one also, you have the higher bandwidth. You have high bandwidth, and the sword normally you use a laser here. And this one you can use a LED emitting diode here. Now you talk about the difference between the single mode and multimode. Remember that single mode you can transmit a longer distance, 100 kilometers. This one only 2 kilometers here. The second one bandwidth. This one is very high. This one is less here. That is a two mode common difference between the single mode and the multimode here. Now in the case of the multimode here, I should explain it to you more. So you see, in the case of multimode, you see you have more than one ray of light, right? So see, if you have one ray here, it goes straight forward. It goes very fast to reach your destination here, right? But this one here, how about this one? You have reflection here, reflection here, reflection here, reflection here. It takes a long time to reach one. So the thing is that the difference between the signal when it comes to destination, they call it the dispersion here. Dispersion. And the higher dispersion, the lower quality of signal it is. The distortion of the signal here. So think about this one, right? You want to say hello to someone here, right? You want to say hello here. So think about this one, the H here. This one L here, and this one L here. So see, H come here, right? And it wait a long time, you have L and something here. I think hello, it's good, but you see, hello. It's not make sense, right? That's why that they call it the dispersion here. And that's why in the multimode here, you cannot transmit a long distance here. Otherwise, you have a huge problem with the dispersion here. And the signal totally distorted here. It makes sense?
Yeah.
Now, you have the difference between the fiber or copper here. So what do you think when you compare the fiber and copper cable together? What do you think? What is the more significant difference here? What do you think?
Right.
Yeah, price. Sorry. Fiber price, of course. It is more expensive, right? It's more expensive. Anything else?
It's a lot faster.
Yeah, you have the higher bandwidth here, right? Think about bandwidth, you have the higher bandwidth in the fiber here. Anything else?
This form, you know, this form.
Anything else?
Not widely is used. Not widely is used.
Nowadays, both of them is widely. Cable very.
Like, I mean, like for, you know, you might have it in a server room, but for copper wire, you're going to have it for a longer distance.
Copper cable?
Yeah.
No, in the longer distance here, you use optical cable. Not the copper, in the long distance, you use the fiber here. Because the copper here, you see, it cannot transmit more than 100 meters. It's this one here, right? So normally you see, in order to connect it from here to the Indianapolis or from intercontinental, they use the fiber cable here, not the copper cable.
It do not deform the signal.
The fiber here, you see, it works with the light. It works with the light. Totally immune to the external interference. So it have no impact with the electromagnetic interference. It have no impact to the radio frequency interference here. So see, the quality here is higher because it totally immune, right? You have totally immune to the external interference. And that's why it works very good with the long distance here. You see, in the case of the copper cable, you got a lot from the internal interference, right? But for the copper cable, as for the fiber here, totally immune to the electromagnetic and radio frequency. You don't have anything impact from the internal noise here. Right? That's why you can transmit by very long distance. Okay, and what else? Okay, and of course, it is the first one is price. It's expensive, right? Bandwidth, higher bandwidth here. And for the internal interference, this one is totally immune, zero. This one a lot, right? This one. And of course, for the installation here, this one you need more technique. This one very simple. And dangerous. This one work with the laser. It's more dangerous. It's really dangerous. Okay, so you learn something about the tool, right? You have the continuity tester. You see how the cable both end work perfectly or not, right? You work with the toner and probe and work with the OTDR. So OTDR, yeah, work with the optical cable here. Okay, so I think that's all for the review. Any question from you? Let me know. Any question?
I don't have any now.
Okay. Okay, so now you know that we work with the physical cable. The physical layer. You can have the copper cable, right? Or you can have the optical cable. And one more option, it can be work with the wireless here. And see, you have the three way to access. It can be the copper cable, can be optical cable, or it can be the wireless here. So this module, by the end of this module, is able to describe the characteristic of wireless transmission, explain the 802.11 standard, everything about the wireless local area network, 802.11 here, and you can plan for the Wi-Fi network, secure a Wi-Fi network, and troubleshoot a Wi-Fi network here. The wireless network or WLAN here, local area network, as a network transmit signal through the air via the radio frequency here. Right? You don't have the cable for this one. You have through the radio frequency. And wireless signal share the many and similarity, including the use of the same layer 3 and higher protocol. So if you remember about the process of the encapsulation, so see when you have data here from the application, when you send it to the transport layer, you have the port number here. When you send it down to the network layer, you have the IP address here, and finally you send it down to the data linker, and you have the header and the channel here. So think here from the performance for the wireless or the copper cable or the optical cable, every upper level here always the same. You see, when they work with the encapsulation, you have the data, encapsulation is the port number, encapsulation is the IP address. The upper level here always the same. The only difference is from the layer 2 here and the layer 1. The layer 1, of course, you have a copper cable, you have optical cable or wireless. So that's why the Y and the wireless signal here share the many similarity, including the use of the same layer 3 and higher protocol. You see, everything from the layer 3 up to the application here, it totally is the same. Here, right? And the nature of the atmosphere makes the wireless transmission different from the Y transmission because you don't have the Y connection here. So you have some definition. The first thing is a wireless spectrum. The wireless spectrum, it is a frequency range. That here you have the definition. That is a frequency range. You have the frequency range of the electromagnetic waves used for the data and the voice communication. The wireless spectrum span frequency in the range band between the 9 kHz and the 300 gigahertz here. So you can think about what is the hertz? Hertz is that you have one fluctuation for 1 second. I think about this one. So if you have a 9 kilohertz here, that means you have 9,000 fluctuation in 1 second. And if you have this one, it's a huge fluctuation here. So that is the way it separates the bandwidth. Sorry, it's a separate the frequency band. Right? So it have to arrange everything from the 9 kilohertz to the 300 gigahertz here. Some band have only single frequency. They call it a fixed frequency here. You can think about this one. The fixed, it always stays the same, exactly the same as this one. It always stays exactly the same as this one. But someone you have the range for that. So we think about this one here. You have the range for that here. Huh? It's not always fixed to one single number, but you can have the span in the range here. And you have some of the most common use you can see in the radio frequency here. The first one, the radio frequency identification. You can think about when you go to supermarket, or you go to the library, right? So if you see each of the book here, you have a tag for that. And a barcode, right? You have a barcode for that. This one here is the most common use for the inventory management here. So we work in library. You can have a reader and you look it up in the barcode here. You look it up in the barcode and you have a reader here, and you can see how many books you have in the library and how many is rent out and how many you have available here. The second one, you have the near-end communication. It's a thing about when you go to the supermarket and you have Apple Pay or you have Google Pay, right? So you use that move it to the reader and it can read it from there. Okay, so we see they have the tag here. Actually, in that you have the something about the barcode, or you have the transmitter here to read it here. Okay, now we have the wireless spectrum. You have the Z-Wave, is a smart home protocol that provides the two basic type functions. You have the signaling to manage the wireless connection and control, transmit data and the command between the device. So think about you have the HVAC control, right? You have the thermostat here. Nowadays you have the smart home, right? So each of them they have specific IP address, and you can control it by the phone here. I can control by the phone, and that's why you can use a Z-Wave here. It is a protocol in order to able to control for the smart home device. Can be a thermostat or HVAC or even that the light or the door, smart door also. Right? Yeah. And normally they have the network controller here. The network controller is where you receive the control information. It can come from your computer or it can come from smartphone. Yeah. And that when you receive the control information, it connects to the smart device here, and it can tell that you have to reduce the temperature or increase the humidity here, or turn on light, turn off light here. Okay, the ZigBee also is allowed. Remember that for everything here is very, very low power, right? And normally they have very, very simple communication here. It's very, very little information, right? Just turn on, turn off, or change it here. Very small amount of data. Normally for this one is always a small amount of data here. And the Bluetooth is a technology that unites a separate entity and a single communication standard. Bluetooth hop between frequency within the band that have to reduce interference, and most Bluetooth device require close proximity. You will have to close distance away, right? And you have ANT plus. Its technology is based on ANT protocol, which is an ad hoc wireless protocol, and uses at 2.4 gigahertz here. And also this one gather and check information about the sensor. You have something about sensor and to work in the medical here to measure the heart rate or the GPS device or other activity monitoring device here.
Like iWatch.
Yeah, that's something that.
iWatch use ANT.
Yes. And you have the wireless spectrum. You can have the infrared here. It's also, but for the infrared also, you need to have the proximity here. I don't want to go in details this one, honestly, I am so not expert on this one. That's why. Okay, so we see that you have the wireless spectrum here. You have the huge range. You have the huge range from the. You see, this one only from 100 gigahertz. You can go up to the 300 gigahertz, and it depends. It depends on the frequency band, and it can go to specific application and service here. So we think about this one here, radio here, very low frequency here. Right? So we can have the Z-Wave and FM radio here. Right? And this one here is a cell phone. This one is a cell phone here. This one here is for the cell phone. This one is for the cell phone. And this one also, you have another band for the cell phone. This one, you have the 5 gigahertz here. You have the wireless Wi-Fi here. You have the wireless Wi-Fi here. And you have the satellite here for this one.
What they call 5G?
What is it?
Cell phone 5G.
Cell phone, you have the, for the cell phone, you have the, actually for the cell phone, you have the 3 bands of the first one is here around 900 megabits per second. Sorry, 900 hertz here, megahertz here. And the second one, you have the 1.9 gigahertz. 1.9 gigahertz. You have, sorry, you only have the 2.1 here. 2.1 here. And this one is for the satellite here. This one for the satellite. Right? You have the satellite for the communication here, and this one in red here. So it depends. It depends on the range of frequency, and you see that sometimes you have the interference here. If you have the frequency bands that's too close together, you have interference here. Okay, so we also have the channel. We have the channel management. The most widely device implement on one of the 2 technologies. The first one is frequency hopping spread spectrum, and the second one is direct sequence spectrum here. Let me open the video here so we can understand what is the frequency hopping spread spectrum and what the direct frequency.
SS works. Second, we also divide data travel time into smaller time units or segment frequency channels. With skip that demonstrate how data travel T1 T2 each time. Now, to see the data instead is much like a mind. The data F5 channel just one data segments. 5, 6. First, spectrum technique introduced in 802.11 base version. It uses spread spectrum techniques by which a signal generated within a particular bandwidth is deliberately spread within the frequency band. And
okay, so the definition here, you see, when you work with frequency hopping here, when you work with a frequency, when you work with a frequency hopping, you see, you have deliberately here spread within the frequency band. So we think that when you have the frequency band, right? So we have from the low point to the high point here. Think about you have this one you have the 900 megahertz, right? And this one you have this one 800 and this one 900 megahertz here. So in the case of the frequency hopping here, you deliberately spread within the frequency band. So you want to transmit along the wave band here, not only one specific frequency here. The thing is that if you transmit at a specific frequency here, what do you think? If you always stick at 580 here, so what do you think? What's the problem with the frequency here? Any idea? Now, if you fix the 580 here, you have something and might happen here, right? What if that you have the another device and next view they work at the 255 here, very close together, right? So in that case, you totally got the interference, the noise here. That's the thing, right? But the thing here, when you spread it out, at one time you have 110, other time you have 190, and other time you have 140 here. You not totally got impact from the interference. That's the first one. The second one is that if you always stick into the same frequency here, you have huge problem of security. I see if you have the radio guys here, he can stick it to the 50 here, and he can easily see what is going on in the networking. He work with the same. He work with the same frequency, and if he have the frequency receiver, he can see what is going on. So see, every time you change the frequency here, you change it randomly. It's actually not really randomly, but they call it pseudo random here. So every time, one time the 110 here, other time 890 here, and other time the 840 here. It's very hard for someone to hijack into the networking.
Is deliberately spread within the frequency band, and thus to reduce interference and jamming, and most importantly, to prevent detection and interception. Now, let's look at how it works. First, let's divide the 2.4 GHz frequency band into 79 narrow frequency channels, and each channel is 1 MHz wide. Starting from the bottom, we label each channel with F1, F2, F3, F4, 5, 6, and so on. Let's skip the rest. We will use these 6 narrow channels to demonstrate how FHSS works. Second, we also divide data travel time into smaller time units or segments, and we label them with T1, T2, T3, 4, 5, 6, 7, and so on. We skip the rest. Each tiny segment is called hop time or hop time. Now, let's take a look at just one data packet, which is moving from a sender to a receiver. During a certain time period, we will see the data packet will not travel through one fixed channel. Instead, it will hop up and down to multiple different channels. It's much like a monkey jumping from a tree branch to another in a jungle. For example, during the T1 segment, the data packet travels through the F2 channel, and then at the T2 segment, it leaps to F5 channel and travels through the channel during the whole T2 segment, and then jumps down to the F3 channel and then leaps up to F6 channel. During T5 segment, it jumps down to F1 channel and then hops up back to F6 channel, and then jumps down to F4 channel. Well, enough jumping and hopping. Now let's freeze the time at F4 channel so that we can see the hopping pattern so far. From T1 through T7, the hopping pattern is F2, F5, F3, F6, F1, F6 again, and then F4. From the demonstration, we could see why this type of transmission method is called frequency hopping spread spectrum. FHSS sends data on one frequency at a time and uses different frequencies over the time. Hopping pattern is known only to receiver and sender, and different senders use different hopping pattern at a different time. This type of modulation method was not only used in IEEE 802.11 base version, but also used by military, cordless phone, GPS, and some other wireless communications. I hope this video is helpful. Thank you very much and see you next time. Oh, don't
Okay,
forget.
so that is the case of the frequency, right? They deliberately hopping each other in random behavior. Now the second one you have the direct sequence spectrum here. I think this one. Yes, this one.
Welcome to Smartsheet. The new world of hybrid work is open for business. Your best and brightest need to be aligned in their system.
I talked about in my last video, DSSS also uses spread spectrum technology. With spread spectrum, narrowband signals are intentionally spread over a much wider band. FHSS uses hopping to spread data signals, while DSSS combines data signal directly with a high bitrate sequence. Let me use 3 simple examples in this lesson to explain how DSSS works. Let's see the first example, a very simple and general process. At the sending end, original data are going into a spreading modulator. Pseudo noise or PN sequence is added and mixed in the spreading modulator. PN sequence or PN code, or we simply call chips, are much higher bitrate sequence, a series of zeros and ones. These chips make original data signals identical to PN code, close to noise level signals. The spreading modulator distributes the transmitted signals over a much wider band. At the receiving end, these transmitted signals are demodulated with PN code and the original data are restored. In the process of modulation and demodulation, 2 goals are achieved. 1. Each bit is coded. 2. Signals bits are distributed over a much wider frequency band. Then what's really going on inside the black box modulator or demodulator? Let's see the second example to pick at some secrets, not all secrets, how PN code works on original data bit by bit. Suppose we send 2-bit data, 1 and 0. In order to encode our original signals, we want to add some noises, which are
called the pseudo noise, and they deliberately add the noise here.
PN sequence or chips, like this long series 1s and 0s.
Okay, so we see from the 1 bit here. So 1 bit here, you convert it to 1, 2, 3, 4, 5, 6, 7, 8, and 9. Deliberately convert it. So the reason that they want to convert it, they want to spread out the signal here. They spread out the signal. So basically, if you don't spread out the signal, here, those signals that's basically if you don't spread out the spectrum here, the signal is located in the range of the frequency here. But when you spread it out, now you spread it out in the huge range of this one here. So we see when you use a huge range of set, you have less chance of interference here.
Keep in mind, PA encode has much higher bit rate than the original data, 1 and 0. Now we will use this exclusive OR truth table to calculate so that we can get encoded and modulated transmitted signals. 1 and 1 is 0, 1 and 1 is 0 again, 0 and 1 is 1. We use the same calculation method to get transmitted signal for bit 1. By the same
So we see original here, you have one bit here. Now, in order to deliver, you have to convert it into rating.
principle, for bit 0, we use the same table again. 1 and 0 is 1, 1 and 0 is 1 again, 0 and 0 is 0, and so on. Now we get our transmitted signals, the combination of original data and PA encode. From this example, you might notice the PA encode consists a radio pulse that is much shorter in duration than the original data signal, like 10 times shorter. The smaller this duration, the larger the bandwidth, the resulting DSSS signals. You might say, I understand the encoding part, however, I do not understand why spreading signals over spectrum could resist better against interference, jamming, and detection. Now let's see the third animation. The red area represents narrowband. Narrowband is easily jammed or interfered. When we're driving on a single-lane road in a rush hour, we might move much slower and possibly get more accidents. In narrowband wireless communications, more power is required to overcome jamming and interference. After spreading, narrowband signals now take much larger bandwidth. The power is still the same, but power density is spread out, resulting in a lower power and noise-like signals, making it harder to interfere and detect. In summary, DSSS has 3 benefits. 1. More bandwidth is used. 2. Data are encoded. And 3. Low power density and noise-like signals are harder to detect and interfered. These benefits could explain why spread spectrum technology and DSSS were developed and used, and are still used in military communications in the first place. I hope this video is helpful.
Okay, so in order to do with the communication in the wireless, whatever it is, you always need the antenna here. Antenna is the one you can transmit the signal or you can receive the signal here. So the wireless signal originates from the electrical current traveling along the connector. So normally you think about if you have something to transmit, right? You have the device here. You have the device. Right? So normally you have the connector here. Right? You have a connector and you connect it to the antenna here. Right? And antenna is everything in the frequency here, in the wireless communication here. And the electrical signal travel along from the transmitter. You can think about this one, the transmitter here, to the antenna, which then emit the signal at a series of the electromagnetic waves into the atmosphere here. And at the definition, right? At the definition here, you receive this one and you convert it to the original signal here. And in order to have the successful communication, the 2 antenna here, they must be tuned to the same frequency. You only have the same frequency. So we transmit this one at the 250 here. This one also we have the 250 here. You only have to work with the same frequency in order to use the same channel here. And antenna radiation pattern describes the relative strength over the 3-dimensional area of the electromagnetic energy as an antenna send or receiver here. And basically, you have the two most common type of the antenna. The first one is directional. Directional, that means you transmit it on the specific direction. So we can think about when you go along the highway, and along the highway here, so they have antenna here. They want it to go as far as it can along the highway. That's why you have the directional antenna here. But you can think about in the home here, you want to have the wireless access. That is omnidirectional. It send it to every direction equally. Send it equally here. I think about here, you have the omni here. You send it to the every direction equally in the chain of signal. But in the case of directional here, you have the antenna and you will just one along with the one direction away. So we can travel along way here. So it depends, right? So think about if you go all along the highway here, you need to use the directional here. You don't need, you see, if you have highway here, you want to do it along the highway. You don't want to go to the rural area here, right? That's why it gets a weaker signal here. And if you go with the directional, you cannot along the way here. You don't need something about signal here. You don't need the signal here, right? Because it is a thing about rural area. You don't need. But you think about in the case of the you have the home internet access here. You want to send it to every corner. Right? Yeah, that's why you use Omni here. Okay. And the geographical area that the antenna can reach is known as a range. A range, that means you see you have antenna here, how far it can reach you, right? So some is limited in the range only. Now we have the signal propagation. Propagation refers the way in which a wave travel from the one point to another here, and in the perfect condition, you expect for the line of sight here. Line of sight, that means you have no obstacle between them, right? So we think about you have one transmitter antenna here, and you have the receiver antenna here. This is the line of sight because you can see directly together, and no one between them, no obstacle here, right? So wireless signal here is not always usually follow the straight line. See, somehow we have the building here, right? In between them, or in the home wireless here also you have a wall, right? You have the cabinet here. It not always follow. So in that say you can have many ways to go. We can have a refraction, or so when the obstacle in the signal way, the signal can be pass through the object. So we think in the dry wall, it's very easy to pass through the dry wall. But in the concrete, the wall is very hard, right? It's very hard here. Or it can be absorbed by the object here. So we think about if you have the tank of water here, it's very easy to absorb the signal strength here. Okay, now attenuation the same with the cable, right? The longer you transmit it, the long range you transmit it, the weaker signal it is. In that case, you can use the wireless range extender here or repeater here. Right? You just regenerate it to the original and transmit it here. The fading, as the signal run into the obstacle here, its energy will be gradually fade. Right? Whenever you see the obstacle here, you got the weaker signal here. Or you have the interference. That is the most common in the wireless because it's open here. It's wide open, and it's very easy to got interfere by the external interference here. It can be from the any machine here, and it's very vulnerable to the noise because it's easy got the interference. And in order to measure how strong signal it is, they use that signal to noise ratio here. Signal to noise, so we can see what is the proportion of the noise to the strength of the signal here. And you have the reflection, scattering, and diffraction here. All of them is the definition. I think that you can watch the video here to really tell what is the difference between them.
You want to be an IT pro, So you must have all of these tools.
Hello, and this is Sunny. Welcome back. In a perfect world, a wireless signal would travel directly in a straight line from its transmitter to its receiver. This type of propagation, known as line of sight, uses the least amount of energy and results in the reception of the clearest possible signal. But in reality, many factors affect signal strength. Taking IEEE 802.11g as an example, the theoretical maximum throughput is 54 megabits per second, but their effective throughput is about half or one-third. What factors make wireless signal attenuation or loss? Absorption. Absorption means some materials will reduce wireless signal's strength and eat up all the potential energy. Brick wall and water are two great absorbers. Different type of wall absorbs signal differently. Dry wall absorbs less than brick wall, and a brick wall absorbs less than concrete wall, and a metal wall is the worst. Besides, other metal appliances like refrigerators absorb wireless signals. Thus, it's a bad idea to put your home wireless router close to your fridge and a big fish tank. Reflection. Reflection is when an electromagnetic wave encounters an obstacle and bounces back towards its source, thus causing loss of signal. Look at this scenario. My computer gets signal not directly from its source, but from reflection from ceiling. Some signals are absorbed by the ceiling, and some signals bounce back towards its source. Therefore, the communication between my computer and a wireless router would be affected. Keep in mind, reflection is not necessarily all bad to wireless signal. Within a room, reflection would help signals to reach its destination ultimately. Without reflection in this case, my computer would not get any signal if we assume the wall blocks all signals to my computer. Diffraction. Diffraction occurs when an electromagnetic wave encounters an obstruction and splits into secondary waves. The secondary waves continue to propagate in the direction in which they were split. If you could see wireless signals being diffracted, they could appear to be bending around the obstacle. Objects with sharp edges, including corners of walls of desks or tables, cause diffraction. Diffraction is easier to understand if we use a creek as an analogy. Without any obstacle, water would flow smoothly. When you threw a stone in the middle, the creek current would split into secondary waves with many directions. Thus, a lot of energy is lost, and the creek water would flow a little bit slower. Scattering. When flashlight being shined against a disco mirror ball, scattering occurs. The same is true for wireless signal. Scattering is diffusion of wireless signal when it encounters object on even surface. When striking on even or rough surface, the mean signal dissipates into multiple reflected signals, which can cause substantial signal downgrade and may even cause a signal loss. Plant leaves, dust, smoke, or micro drops of water in the air can cause possible signal wave to scatter. Last but not least, interference. A variety of household appliances can cause wireless interference, including cordless phones, baby monitors, and microwave ovens. Anything which communicates on the 2.4 GHz frequency can interfere with your home Wi-Fi signals. Even though it's not common for those items to cause the major problems, it could be worth keeping them in mind if you are having problems. There might be more factors affecting the strength of wireless signal, such as distance from AP, antenna's positioning and quality, wireless media access control method, and so on. The 5 factors I mentioned above are more likely to appear in the networking certification tests.
Okay, so we have the definition about the attenuation, daily interference, reflection, scattering, and diffraction here. Okay. Yeah. Oh, now we come to the wireless LAN standard. The wireless work at the IOSI layer 1 and 2. Remember that it's no different between in the upper layer, right? Have no difference in the layer 3, layer 4, and the application here. When you compare with the couple cable here or the optical cable, all of them work from the layer 3 to the upper to the application layer. Always the same. The only difference is in the layer 1 and layer 2 here. So for the wireless local area network, they support the TCP/IP higher layer protocol and the operating system. And the most popular standard used by the wireless LAN, referred as the Wi-Fi, it's wireless here. And you have some standard. You have the, you see everything here is if you see everything about the 802.11, everything about the wireless local network here. It can be the 11B, A, or G, N, or AC, or AXC. I have another video here.
I want to break free.
Almost all of us have devices that use 802.11 wireless networks. It might be our mobile phones, it might be a tablet, or it might be the computer or laptop that we're using. Most of us rely every day on this 802.11 standard that comes from the IEEE 802 Standards Committee. This is one of the most popular wireless technologies in the world, and in this video, we'll step through the evolution of 802.11 wireless networking through the years. When the 802.11 standards were released, there were 2 standards that were released simultaneously. One of these is the 802.11a standard, one of the original standards that was released in October of 1999. 802.11a operated in the 5 gigahertz range and gave us throughputs up to 54 megabits per second. Because 802.11a was using 5 gigahertz frequencies, it tended to have a smaller available range than the 802.11b standard. 802.11b uses 2.4 gigahertz frequencies, and those lower frequencies tend to bounce off of other objects rather than being absorbed by objects at higher frequencies. The 802.11a standard has been replaced by newer 802.11 standards, so you don't tend to see much 802.11a traffic on a network today. The 802.11b standard was released simultaneously with the 802.11a standard in October of 1999. As we've mentioned, it uses the 2.4 gigahertz range to communicate. 802.11b communicated at a maximum possible throughput of 11 megabits per second, which was significantly different than the 54 megabits per second available with 802.11a. But 802.11b gave us effectively longer ranges because those 2.4 gigahertz frequencies would bounce off of objects rather than being absorbed. One challenge with 802.11b and these 2.4 gigahertz frequencies, however, is there are a lot of other devices that are communicating at that frequency. Cordless phones, baby monitors, and Bluetooth communications all operate at 2.4 gigahertz and could potentially create conflicts with the 802.11b communication. 802.11g was introduced in June 2003 and was very similar to 802.11b, and this is considered an upgrade to 802.11b. It operates in the same 2.4 gigahertz range, but the overall throughput was increased to 54 megabits per second, which is very similar to the throughput for 802.11a. This 802.11g standard was backwards compatible with 802.11b, so if you installed an 802.11g access point, it could very easily also accommodate 802.11b clients. But
see that you have the two range of the Wi-Fi here. The first one is a 0.4, sorry, 2.4, and the second one, the 5 gigahertz here. And some of them, they are not totally compatible together. So if you have device only work with the 2.4, it cannot work with the device work with the 5 gigahertz here. Right? So see, in the case of A, it works with the 5 gigahertz, but in the case of B here, it works only with the 2.4.
you do have the same problem with frequency conflict because you're still communicating in the 2.4 gigahertz frequency range. In October of 2009, we received a big update to the 802.11 standard. This was 802.11n. This was effectively an update for 802.11g, 802.11b, and 802.11a. 802.11n can operate at 5 gigahertz or
So see from this one here, it works both for the 5 gigahertz and 2.4 here. And this one compatible with the A and B and G before. Right? But the thing was that one, the B here is not compatible with A because B here is 2.4 and A here is 5 here.
2.4 gigahertz, and these particular channel widths of 40 megahertz were much larger than the bandwidths available with previous versions of 802.11. 802.11n can support throughputs up to 600 megabits per second using this 40 megahertz channel width and 4 antennas sending multiple streams of data simultaneously. 802.11n was the first version of 802.11 to use multiple input, multiple output, or MIMO, where you're able to send multiple streams of information over the same frequency. You just need multiple antennas and radios to be able to send that data. One of the most recent versions of 802.11 is 802.11ac. This was introduced in January of 2014. 802.11ac operates in the 5 gigahertz band exclusively. There are some 802.11ac routers that you'll see communicating in both 5 gigahertz and 2.4 gigahertz, but all of the 2.4 gigahertz communication is communicating using 802.11n. Because there's no requirement to communicate in the very crowded 2.4 gigahertz band, you can use much larger bandwidths within 5 gigahertz, and 802.11ac supports up to 160 megahertz channel bandwidths. This AC version of 802.11 can also bond together individual channels to effectively create larger channel bandwidths. There's also a denser signaling modulation, which means you can send data much faster. With 8 multi-user MIMO streams on 802.11ac, you can theoretically support almost 7 gigabits per second of throughput on this wireless network. Here's a summary of these 5 standards. 802.11a and b that were released simultaneously. A supported 5 gigahertz and B supported 2.4 gigahertz, and neither of them supported multiple input, multiple output. 802.11a provided 54 megabits of maximum theoretical throughput, and 802.11b supported 11 megabits. 802.11g was an update to 802.11b, and it uses the same frequencies of 2.4 gigahertz, and it increased the speed up to 56 64 megabits per second. 802.11n was the very first introduction of multiple input, multiple output, and you could support up to 4 streams in 802.11n running at either 5 gigahertz or 2.4 gigahertz. Running up to 4 of those 150 megabit MIMO streams, you could support a theoretical maximum of 600 megabits per second with 802.11n. And with 802.11ac running in the 5 gigahertz range, running 8 multi-user MIMO streams, you could support almost 7 gigabits of throughput over this wireless network.
Okay, so he mentioned about the MIMO. The MIMO is the multiple input and multiple output here. So basically, if you are the transmitter and receiver, you only have one channel, right? So at the one time, you are able to transmit for the one channel here. But when you use the MIMO, you have the multiple antenna for both of the transmitter and receiver. So it can increase the throughput in the case of the MIMO.
Lots of vitamins A and C. V8, the original plant-powered drink. Veg up.
With MailChimp's Customer Journey Builder, you can connect with more customers and lead them and their furry friends down a path to purchase.
In this video, we're going to talk about a wireless technology called MU-MIMO, which stands for Multi-User, Multiple Input, Multiple Output. Now, MU-MIMO was introduced with the Wave 2 version of the 802.11 AC wireless standard. And this is a feature that's used in modern Wi-Fi routers. And what this does is that it allows multiple wireless devices to communicate with a Wi-Fi router at the same time. Now, previously, routers communicated with devices using SU-MIMO, which stands for Single User, Multiple Input, Multiple Output. Now, this was used with the previous wireless technology, which was 802.11n. Now, this also allowed Wi-Fi routers to communicate with multiple devices, but only with one device at a time. So each device would have to wait their turn to communicate with the router. So as more devices connected to the Wi-Fi router, congestion happens. Now, this is not really a big deal if these devices were just using low data applications such as browsing the internet. However, if they were using high data applications such as streaming videos, then the result would be a slowdown in the internet speed, which would cause lag and buffering. So basically, single-user MIMO works on a first-come, first-served basis. However, a router that's using multi-user MIMO, all the devices that are connected to it won't have to wait their turn because it allows communication to multiple devices all at the same time. It breaks up the internet bandwidth and pushes it to the connected devices. So, with this technology, you will see a significant improvement in the speed of your internet, especially if you're doing things that require a lot of bandwidth, such as streaming videos or downloading. It reduces lag to the connected devices because the connection is never interrupted, which increases performance. So it's almost as if each device had their own separate Wi-Fi router. So if you have a lot of wireless devices that demand a lot of bandwidth in your home and you're experiencing slow internet performance or choppy video, you should be using a router with multi-user MIMO technology. Now, multi-user MIMO also takes advantage of beamforming. Now, beamforming is a
This one. Okay, so we have some definition, right? You have the word and you have some standard here, AG and AC and AX also. And you have the MIMO, and you have we have some of the innovation that has been implemented that contribute to the later 802.11 here. Some of them we have the orthogonal frequency division multiplexing that support more multi-user here in the IX here. Standard. Okay. This is how we encapsulate it in the frame here. Okay, now we have the access method. Access method is that how can you access to the media, right? So The access method is that we have some definition. You have some definition. That's the thing that the first one is the MAC address. You know that, right? The MAC address is a 48-bit here. And the widely defined and not designed to originally is not designed to simultaneously transmit and receiving. Does that mean you only able to transmit or receiving? Cannot do it at the same time here, right? And the 802.11 standard specifies the use of the CFMACA, that is carrier send multiple access with collision avoidance. So the current sense, that means before you transmit it, you have to listen. You have to listen to the media here to see if idle or not. So when you see it idle, you can transmit it. If not, you have to wait here. Right? But the thing is that in the case of the wireless access here, now let me come back to the history here. I think it should be better. You come. The first definition is CSMA CD here. So CMNA CD, that is a carrier send multiple access with collision, but not avoidance here. This is a detection here. Detection. This one here, CMACA, it works with the path topology. I work with the hub. You see, I show you the hub it work here. So how it work with the CMA CD here? Let me show you something here. Sorry, this one. So back then you can think about the hub as a bus here. You have the cable, right? And in that one, in the single cable here, you share to every computer on the network. You share it to many computers on the network. You see, this one is a share cable. You think about the hub here, right? So see, in that case here, it works as a half loop like. It works as a half loop like here. That means when this one transmit, other one have to listen. Otherwise, you have the collision here, right? So in the case of the hub, they work with the CSMA CD here. That means carrier send multiple access collision detection. So see, whenever you want to send it out, the first step you only have to listen. You have to see if the media here idle or not, free or not. Right? So think about this one. In the case, if this one here listen and he detects that no one transmit here. So now he transmitted. But what happened at the same time? This guy also listen, right? Both of them they listen, and both of them they see that no one transmitted here. So at the same time, you see, at the same time, both of them send it out. So in that case, you have collision. You have collision here, right? In that case, you have collision. That's why you have collision detection here. So in the case of collision detection, in the bus topology here, it works that they work by random time holding random time here. Right? So in the case, any computer detect of the collision, he have to delay it at the random time. Right? So maybe this one here delay for 1 millisecond, and this one here delay for 5 milliseconds here. So after 1 millisecond, this one send it out. Right? Send it out, it's okay. But you see, when after the 5 second here, millisecond here, this one listen again. It's not free anymore. Right? So see, the reason that they have to do it at the random time, because if you see, if both of them wait at the same time, again, you have a collision here. I see, if you wait for 1 millisecond here and wait for 1 millisecond here, and after that you send it again, you have the collision again. Right? So that is the case of the Y connection, So in the case of Y connection, it's very easy for you to detect the collision here. That's why they call it a collision detection. You see, when you send it at the same time on the Y, it's very, very easy for you to detect the collision here. So they call it a carrier send multiple access collision detection when you work with the bus topology and when you work with the hub device here. Now come back to the wireless communication. Wireless communication, you cannot detect it. You only have able to avoid it. Only. So that's why you see in the case of the wireless here, you have the carrier send multiple access with collision, but it's not detection. You avoidance here. You try so bad to avoid here. And you use the acknowledgement packet to verify every transmission and require more overhead than the 802.3. 802.23 is the Ethernet. It's Ethernet, right? And in order to do everything with the collision avoidance here, you have to use a request to send and clear to send. Before you send, you have to request to send. You have to listen if someone is free or not, right? And if you got the approve from the access point, you go approve from access point. After that, you can send it here. Okay, so we see that is about you work with the request to send and the clear to send here, right? So see the first step here, always listen here, right? Check the transmission here, and if you detect activity, you have to stop it, right? You have to pause here. You have to pause and again listen again, right? And again, if you don't detect any activity, you send the request to send it. You send it to the access point here, right? And access point is who control every communication here. And if you got the confirm clear to send, if you got a clear to send, you're able to send it. Right? If not, again, you have to hold on. You have to wait until the term. Okay, so you have the association and wireless topology, and so association is a process where the packet are exchanged between the computer and the access point. You know that for every home wireless communication, you have the access point, right? Access point is that one you communicate with every single device here, and the one who connect with the internet here. Okay, the scanning occurs when the wireless device surveys surrounding access point. You see when you go to the area, you have the wireless internet, right? The cell phone or the laptop or iPad is able to detect it, and that's the thing is that it's able to do is scanning here. So whenever you go to the area that you have the wireless signal, can able to detect it here. And in the case of the detect, you have the two types. The detect here. The first one is the active scanning. Sorry, in the case scanning here, you have the active scanning, and you have the you have the passive scanning also. So let's see what is active here and what is the passive here.
I think Shopify has definitely helped us and many businesses get started. Actually, my wife, she was the one that brought it to me.
Active scanning and passive scanning. In active scanning, a wireless device broadcasts a probe, a special type of frame, to each channel in its frequency range and waits for the AP to respond. Active scanning means the wireless device or client initiate the search effort. Let's say the process of active scanning in simplified version. We skip authentication and encryption steps here simply to focus on the active scanning method for wireless association. Wireless client is sending a probe continuously to scan for an AP. This is step 1. In this example, both AP1 and AP2 hear the probe and respond with sending their SSIDs and other information to the device. And this is step 2. The device sends its request for association with AP2, which might have stronger signals in this example, and this is step 3. The fourth step, AP2 responds with the confirmation and approval of association. The wireless device can get full access to the network through AP2. The device sends its request for the full association access.
Okay, so we see in the case active scanning, the computer or the device is the one who actively scans the network. He scans the network and he type if you have any available network here. So when you got the response from the access point, you are the one who requests for the association here. That's why the code is active. Now is the case
to the network, not initiate the search effort. Instead, it simply sits back.
Okay. Now in the active scanning, you are the one, the device, the one who actively scan. But in the case of passive, you just passively listen it. You just sit back here, sit back and listen the advertising from the available channel from the access point here.
And it just listens on all available channels within a frequency range for available APs. An AP broadcasts a beacon frame continuously to its service area. This special frame, beacon, contains AP's information such as SSID, which is also known network name.
ID is the network name. As you can see now, if you scan, you can see you have the IP guest here. That is the ID. It tells you what is the network name.
Here is the process of wireless association with the passive scanning method. Again, we will skip authentication and encryption steps just to focus on scanning process for the association. Here we are. Both AP1 and AP2 continuously broadcast their beacons to all available channels within the frequency range in their service areas. Beacon.
Okay, so when he broadcast, he has some information about what is the frequency range and what is the channel here. Right? And you are the one who passively listen to it. You don't actively scan it. Oh, sorry.
Frame contains information such as SSID. This is step 1. A wireless device listens on all channels for beacons. The device can choose which AP to associate with. Suppose this time device choose AP1. It sends request for its association with AP1. This is the second step. AP1 responds with approval of association, and this is the third step. Now, the device can get a full access to the network. Reassociation and roaming. What happens if the wireless device moves from one AP to another within one extended service set, ESS?
This one we mentioned it later. So now we just know the difference between the active that means you and device. You can think about you have the cell phone or you have the iPad. You have to actively scan what access point you are able to access it here. And it's a clear passive that you are just sitting back here and you got every advertising message from the access point here. Okay, so we have some definition about independent basic service set. You have the basic service set and you have the extended service set here. Okay, so you see about in the case of the independent here, you have the group of the end device and user directly communicate together. You see there is that group of the devices communicate together. They call it the ad hoc here. And this one you have the infrastructure wireless local network. In that one you have one access point here. Right? Think about in the home, you have one access point, and actually in the home you have the access point and the router or the switch they are integrated in one device. Right? Normally you see it, everything here. It's saying, when we talk about home router, actually it is access point because to work with the wireless access. It works with the switch also, right? You can plug in the wire connection, right? And it's a router because it interface with the internet. So basically, the home router, it is an integrated device. You have the router function, you have the switch function, and you have the access point function. Okay. Now, in the case of infrastructure wireless LAN here, you have the access point and who control every access from the every end device here, wirelessly connected to it here. Now, this is the case of the extended service here. So see, in that case here, you have more than one access point. The thing with the campus here, you have more than one access point, right? So in that case here, you can freely roaming from one access point here in the area here. You can freely roaming to another access point or move to the another access point here, and they interconnect them together. And all of them, they share the same name. You can think about this one, right? You see, when you go to the cell phone here, you see the SID here, and SID, that means you have the service ID here. That means it's a network name. You can see for this one, you can see it's the IP address here, right? So see, actually in this campus here, you have multiple access point. You have multiple access point, but all of them share the same name with the network name here, IP address here, and you can freely roaming between them together without the interruption here. Okay, and it's how about the IEEE 802.111 frame, and how it work with the frame here? Is the key? You think about this one. You have this one is a media access control here, header here. How we encapsulate the frame in the 802.11 here. You see it different between the when you work with the Ethernet, right? Ethernet is the wire connection. You only have the one field for the source address and one field for the definite address here. But you see, in the case of wireless, the way it encapsulates is not the same. You have more field, you have more address here, address 1, address 2, and 3, and so on. Okay, what type identifier allows the wireless client to roam freely from the access point to access point? What do you think? Yeah, extended. You have the extended here. This one is extended. This one in infrastructure here. That means, sorry, this one IP address. This one is a base. You only have one access point. Okay. Now, how can you implement a Wi-Fi network? Wi-Fi network here. The first one, you have to determine the design, right? So in the case of the design here, the most important thing that you have to do about the site survey. Site survey, that means where you locate the access point, right? So that to make sure that every corner in the range of the coverage here, right? Okay, so the access point normally in the home here, it combines with the switching, routing, and other network function. So in the home router, you have the access point, you have the routing, you have the switching. All of them, they are integrated in one single device here. Okay, now when you design the wireless, you have to consider for some things. The first one, the distance. Right? So what happens if the range is too short? You are not able to access the here, or you have to consider about the time and the number of the obstacle here. So think about in the case of the concrete wall, it totally blocks the signal here. Right? But in the case of dry wall, it's okay. Not much here, and you think about the coverage interference also. Interference, it's really challenging in the wireless network here because it's very easy to get interference from the electromagnetic machine here. Okay, so that's it. The site survey is very important. The site normally when you design the wireless here, you have the special tool. You have special tool, so you can show you where you locate the access point, and when you move around, you can measure how strong the signal it is. So based on that, you can see from which point you can locate the access point here. Everything here is only a definition. You cannot go into detail for this one, for this class here. And okay, for site survey, you have to study the building blueprint and identify the potential obstacle here, where the Wi-Fi access point, access the wireless bridge, or to create more wide connection floor. You have to measure signal coverage stemming from the other wireless LAN also. You have to test proposed access point location. You have to test the wireless access point from the positive corner, from the positive corner of the space here, right? Because you have to go to the positive point to see how the channel of the signal is. And you have to think about the material used in objects, how we represent the environment, how the wireless portion of the LAN integrate in the wide portion here. So basically, in the enterprise scale wireless network here, they can break it down in the each of the floor or each of the room. You can have the one access point, and they interconnect them together here. And for when you configure the Wi-Fi connectivity device, the access point is vary in which the wireless standards they support, antenna strength and other feature. You have a variable set during the installation includes the administrator password. So whenever you want to configure for the password, or when you to do with the access list here, you need administrator password. So I believe that some of you already configure the home router, right? You just plug in the cable and you change the password, and then you can do some with the security here. And sometimes someone you want to advertise on network name or not, it's up to you, right? So we see that when you don't advertise, when you do not broadcast the network ID here, no one able to scan and see your network here, right? And think about this one, right? In the home, if you want to broadcast here, think about my network, my Wi-Fi here. I said it is network number 1 here. Network number 1 here. So basically, by default, it broadcasts. So see when I have the cell phone, I go to the coverage of my network here. I scan it, and I can detect that now I have the network number 1 available. But in the case, you can disable the broadcast here. So if you want to access it, you have to manually enter the network name here. Is the network 1 here. You have to manually enter it. Right? And also, you have the security option also. You have the security option. So for the security, you can set the password, or you can work with the access list here. Now think about this one here, right? You see, in order to access to the wireless network, each of the network interface card, you have the specific MAC address here, right? So based on security here, you can filter, you can make a filter for that. You can make a filter for that. So think about if your computer A here, you allow it. You can allow it, but the computer B here, you do not allow it. It's based on the MAC address filter here. Or you can decide whether or not the DCP used or not. DCP is a dynamic host compression protocol. That means you can give the IP address automatically to every device. You can automatically get the IP address.
I refuse to give the DCP. Can they still log in the internet?
You have to manually configure. In order to access the internet, you must have the IP address here. And in order to have the IP address, you have 2 ways to do that. The first one, you have to manually configure. The second one, you got it automatically from the DCP server. Okay. Okay, so when you configure the client, you can have the client here. Now, if the access point broadcasting is SAE, right? So the client definitely he can detect it. He can scan and see here. Okay, so onboarding, you can install the specific program or app on the device to give it chartered access to the certain portion of the network, or you have the offboarding. You can involve the removing program that gives the device special permission on the network here. What else? Okay, now we move to the Wi-Fi security here, network security here. So that's one very, very hot topic here.
Let's do great things. One.
Hello everyone. In this video, we're going to talk about the different wireless security methods and protocols that are used in wireless networks. Now, most of us have connected to a Wi-Fi network with our laptop, tablet, or even our smartphone. And to join that network with our device, you had to select the network name and you had to supply a password. Now, Wi-Fi networks can be just open with no password required. So that means that anybody can join it. However, in the majority of cases, Wi-Fi networks will be secure and will require a password. Now, there are several different protocols that are used for securing a Wi-Fi network. So let's start with a secure protocol called WEP. WEP, or Wired Equivalent Privacy, was developed in 1999, and it's the earliest security protocol that was used for wireless networks. And also, as its name implies, it's meant to supply the same security to wireless networks as it did for wired networks. However, this turned out not to be the case, because after a time, it was found out that the 40-bit encryption key that WEP used was vulnerable and not secure, and therefore it was easily hackable. So that's why today WEP is no longer used, and modern Wi-Fi routers won't even have it as an option anymore. So a better security protocol was needed for wireless networks. And that brings us to WPA. WPA, or Wi-Fi Protected Access, is another wireless security protocol that was developed to solve the problems of WEP. WPA is far better than WEP, and this is because it uses a stronger encryption method called TKIP, which stands for Temporal Key Integrity Protocol. And TKIP dynamically changes its keys as it's being used, and this ensures data integrity. But even though WPA is more secure than WEP, even today WPA is outdated, because TKIP did have some vulnerabilities. And that brings us to WPA2. WPA2 was developed to provide even stronger security than WPA, and it does this by requiring the use of a stronger encryption method. While WPA uses TKIP for encryption, which is known to have some limitations, WPA2 uses AES.
So in one of the assignment you asked about the difference between the TKIP. One of the assignment you have the difference between the TKIP and the AES here. So remember that this one is more secure when you compare to this one.
Which stands for Advanced Encryption Standard. AES uses a symmetric encryption algorithm which makes it strong enough to resist a brute force attack. In fact, AES is so secure that the U.S. federal government has adopted it and is now using it to encrypt sensitive government data. Now, when you log into the Wi-Fi router's configuration page and you go into the Wi-Fi security section, this is where you would find the different security protocols that you can choose from to protect.
This video is quite outdated. Actually, nowadays they also have the WPA3 also, more secure.
Your Wi-Fi network. So here is an example from an older Linksys router. And here you can see the WEP, WPA, and WPA2 protocols that we discussed. Now, as I said, this router is a few years old, and it still has WEP as an option. However, newer routers, like this one here, won't even have WEP as an option, because WEP is weak and outdated and is no longer used. And thank God for that, because it was garbage.
Basically now WPA2 is the most common. And remember that when you work with the AES, it's more secure when you compare to the TK-IP here. Okay, so that's about the definition only. So, okay, in the case of the MAC filtering also, you can prevent access from the authenticating for any device with MAC address is not needed. You can filter, make a filter. What else? Okay, so yeah, you have the sum of the definition where you do it in the video here. This one is the most common now, WPA2 here. And you see, it's a faster and more secure encryption than the TKP here, right? AES here. Okay, so now we have when we work with the security, you also have the definition about the personal and enterprise here. So think about the home, right? About the home access point here. You think about in the home access point. You set the password here, right? You can set the password. You take the X, Y, Z, D, whatever, right? They call this one the pre-share. Pre-share here. Pre-share. What is pre-share? That means everyone has the same password. You see, you have the same, right? Whenever you have the laptop or desktop or the cell phone, you or your wife, whenever you want to go to the internet, wireless here, you enter the same password. You enter the same password. You see, you think about it in the environment, you have the large company here. You have hundreds of the employees here. Totally not secure, right? Totally not secure. Everyone has to share the same password here. So in that case, you have to work with the WPA enterprise here. So in the case of that WPA enterprise, they have to work with a dedicated server. You have to insert. You see, when you have think about this one, you have the router here, you have the switch here, or you have access point here. All of them route to the dedicated server here. They call it the radius server here. Right? So they use with not radius server. They call it AAA here. AAA, that means you have the authenticating, authorization and authentication. They have authenticating. Sorry, sorry. What is it? Accounting, authentication, and authorization. That's why they call it a AAA. Accounting, that means it keeps track of what time you log in, what time you log out, and everything about the billing here, right? How much money, right? You can think about this one. Authentication is that means you have to verify what is your username and what is the password, right? What is the name of the password? Authorization is that to which level you can change the password, to which level you can interfere with the network here. Some of you can control everything if you are the network administrator, right? But if you are the employee, you have no way to control everything here. So in the case of the enterprise here, so we see whenever you log in the access point or router or the switch, it route it to the AAA here. It's routed to AAA by the protocol here, remote authentication 19 service here. So whenever you want to access here, if you are the cell phone or if you want to access to the access point here, the access point query it to the database stored in the dedicated server here, and he say, hey, please enter what is your username and what is the password here. You enter it, and he queries this one. This one give you here. Confirm you are correct or not. That is in case of the enterprise here. So we see each of the user, they have specific username and password, not only the same. You have the specific username and password. You and Joe White, not the same. That is in case of enterprise here. Okay. Okay, so that is the case here. You have the server here. Whenever you access to the network, it requires you to enter the username and password here. Okay, you also have other security configuration. You can have the access point and antenna placement, geo fencing, gas network, wireless client isolation, captive pattern or IoT access configuration here. We don't have to go into detail for this one. And you have the security threat to the Wi-Fi network. You have the word driving. The hacker search for the unprotected wireless network by driving around. I see you have special tool, and you can driving around, and he can detect what is the available network, and you can see if the password is weak or not, or no password here. He can have a word chalking. The hacker draws the symbol with the chalk on the sidewalk or near the vulnerable access point to know for the other hacker here. This one is the most common here, even Tran. So think about in the evil Tran that it set exactly the name here. For this one here. Now, if you have the valid network here, you put it's a network number 1 here. Network number 1. You set the name of the network number 1 here. But the bad guy here, again, he make it up for the another access point, and he set exactly the name, network 1 here. So it's very, very misleading here. So instead of going to the correct one, you go to the bad guy here. That's why they call it the evil twin, because you have the same name. And you have the WPA attacks that involve the interception of the network key, communication between stations here, and that's why you always have to use the most secure and most update encryption here. I think about this one. Nowadays you have to use the WPA2 instead of WPA here. Okay. Okay, you have some of the Wi-Fi network tool. That everything about definition, I don't have the tool to show you. That's why. Yeah, you have the tool type, the software. You can have the spectrum analyzer, very helpful for you in the cable, the side server here. You can see that when you move around, you can see what is the channel of the wireless signal here. Or you can have the wireless analyzer software that can evaluate the wireless network ability and optimize the signal setting. Okay, you have some of the capability common for the wireless set tool here. And you can find the information in the book. It's everything about here is the definition. I don't have something to avoid you here. To show it here. Okay, so I think that's all for the lecture here. Let's see what you have for the homework. Any question from you? Hello?
I don't have any.
Okay, this one is very straightforward here. This one you can think about you configure with the home router. If you have the interface and you log in the home router, and you can change, you can make the change with the, you can do some change with the password setting, and you can change about the DHCP setting also. This one is very straightforward, and it's very helpful when you want to configure your home router here. And so basically, you see that in order to configure the home router, right, you need to plug in the cable into the home router. And normally the default IP address is 192.168.0.1 here. And when you configure that, you have the interface to ask you to enter the username and password. And username and password here is the default. It's admin here, and username and password here. And so after you log it in, you can change the username and password to make it more secure. What is it? So we see for this one, when you enter the 192.168.0.1, actually you log into the interface of the router here. So for this one, you have admin here. You log in. See, that is the interface that the same way to work with our home router here. So with this one, you can have the sum of the basic information. You can do some of the basic configuration here. What is it? Let's see. Set the time zone. Why I'm not able to change it? Yeah, this one. Okay, so this one is very, very straightforward here. I don't want to go into detail for this one. Why I'm not able to skip here? Skip. Now you see, when you go to the home router, right? You are able to change the name of the home router here. That is NNID. Sorry, NNID here. You can change the name. You can change it. For this one, you have to change this one, and you are able to change the password here. So anytime if you want to access to the wireless network, you have to enter the password here. What else? Okay. What else? That is admin network. Okay, so we see that also you are able to change about the what is it? We call it the standard, right? You can have the A, or can have B, or you can have G or N or IC here. It's up to you. You can set it here. Okay, so I think this one is very, very straightforward. I don't want to go into detail for this one, but it's very helpful when you work with the home router here. You can do the same with the home router. Okay, this one also. You have the simulation here. You work with the home router. Now we have the two capstone project here. When we work with the packages here. First one is the 6.6 here. Okay, so for the system one, you have to create and secure basic wireless network in the packages. It is also very, very, very straightforward for this one. You have to drag and drop. You have to go drag and drop here. This one is a wireless access point here. That's one is a wireless access point. So let me save it and then open the new one here. So in order to go with the wireless access point, you go to the network device here. You go to the network device. So what is it? This one, the hub. This one, yeah. This one, wireless access point, and you work with this one. Sorry. Yeah. They are asking you to work with the where. This one. You see, this is a wireless access point. This is router, and it's a switch, and then wireless access point for antenna here. Right? So it's that guy, right? And you go to the if you want to configure it, right? You go to the config tab. You have to set the IP address and the subnet part here. So in that case, you click on this one. You go to the config. Right? You have to go to the config and what interface you have to configure it here. So, you have to set the LAN here. The LAN facing IP address. Now you have to configure on the LAN here. You have to put it here, and you have to put the IP address and the subnet part here. Now for the end device, right? So we'll see when is the current end device here. User work with they have to work with the laptop, right? So you go to the end device. You see you have the laptop here. But the thing is that for the laptop, when you click on the physical here, right now you have the wire connection. You have the wire connection here, not the wireless connection, right? So in order to have the wireless connection, you have to plug in the wireless interface here. So in order to do that, you have to turn off the laptop. The first thing you have to turn off the laptop and you plug it out this one, and you plug it in this one here. This one is interface with the wireless here, and you turn it on, and you turn it on. See, instantly you connect it to the internet here, right? Because you have not set up the password yet. That's why it's instantly able to access the to the access point. You can think about this, it's an open network here, and you have problem with security here. Right? Okay, so I think, yeah, this one I will explain it to you, right? This one is more secure. This one is more secure when compared to the TK IP here. And this one. Okay, so in that case, if you want to configure for the security, you choose this one here, personal here. That is a person. It's a home network that work. It's a personal here. Okay, so I think it's not really challenging when you work with the package chaser here. You just follow the step. And anyway, if you need any help, you can ask me on the class, or you can send me an email, or you can join my office hour. You know that I have the office hour. I put it in the syllabus here. Right? And my office hour here is every Tuesday and Thursday from 9 to 11 here. And if you want to join my office hour, you can join the Zoom link here. Any question? Okay, so
no questions.
Okay, so let me check the attendance here. Mark, are you here?
Yeah, I'm here.
Yeah. Tyler?
I'm here.
Anyone here? Are you here? Matthew, are you here?
I'm here.
Okay. Jack, are you here?
Yes, I'm here.
Smith, are you here?
Yes, I'm here.
Thomas, are you here?
Yes.
So, if you have no question, I see you guys on Monday. Okay.
All right. Thank you for your time. See you next Monday.
Thanks. Have a good weekend.
You too. Bye-bye.